we're going to talk about spatial and temporal memory safety in C and C++. So we're going to talk about methods how we can achieve this memory safety using pointers. Pointers are a very common courtesy in C and C++, but there are several issues that can arise when you use pointers in an incorrect manner. We want to enforce the safety of these pointers in time and space, so you cannot use the pointer when it's no longer being used in a correct fashion, when it's already been freed or when you have a dangling pointer. This is called temporal safety. You also have the space aspect of the safety, which is going out of bounds and simply using the wrong pointers at the current time. We want to do this using software-only approach so that you don't need specialized hardware or code adjustments. You can just recompile the existing code and you should be all set to go. First method we will use is Softbound, which is a program that enforces spatial memory safety. Why should we use Softbound? So the policy is securing pointers from going out of bounds. It does this at compile time and it produces as little overhead as possible. It also needs no code adjustments or compiler hinting, so you can just recompile old code. Software only approach, as I mentioned before, and it also has guaranteed bounding, so you can always guarantee that each violation will be noticed and that there also are no false positives. Do we really need this Softbound program? Actually, yes, because buffer overflows are so common attacks and they are so devastating, they can do all kinds of malicious stuff. So using this program in the compiler we can prevent all of these attacks, such as return to libc attacks. Properties of Softbound are that they have source compatibility, so it has to be compatible with all kinds of different source codes. It has to be compatible with all the written programs up to this point. It also provides completeness, so it offers complete protection. And there is also something called separate compilation, which means that each library can be compiled one at a time and then they can be linked and still provide complete safety. This is very much needed for large projects. We have two different modes in Softbound. We have a full check mode, which checks each dereference when it is made and check if it is a legitimate dereference. We also have a store-only check mode, which only does this for the storing operations. The implementation consists of changing a pointer to some kind of fat pointer, but we don't do it in place because this would mess with the memory, such as a struct. You can no longer just count on the size of the pointer being the same. So we need to add two different values. We need to add a base and a bound. The base is the start of the memory that can be read, and the bound is the last bit the first bit that can't be read. We check these base and bounds on each dereference, and with the dereference we include the size so that conversions can't void this security issue. In the implementation we set the extra data in a separate table on each malloc. This is due to the memory constraints in struct and stuff. We also check this on each dereference, but in some situations it isn't needed to dereferences, such as static length arrays. We don't need to check this each time. We know in advance that we will not violate this in the program code. So the compiler removes as much checks as possible to further optimize the code. We also have an option to shrink bounds, but this can cause issues and is not really that much related to the topic of safety. The performance of Softbound is quite well. It stops all the violations and it has no false positives, so this is actually excellent. It does, however, give some overhead in the runtime. On average, it can be 67% extra runtime, but sometimes can go up to a factor of 2.5. In the store-only approach, the overhead is much less, and it's also viable for production in some cases. However, there's also the problem of memory size. On average, it uses 64% more memory, but it can go up to 200% more since each pointer has 3 values. The cache also cripples its performance because of the extra table that needs to be looked up. This can cause the cache miss rate to more than double, but this is highly dependent on the benchmark because some benchmarks don't even need that much lookups to this table because they can be optimized in such ways that it's not needed.
In the second part of this presentation, we'll talk about CETS, which is Compiler Enforced Temporal Safety. The goal of this software is to detect all temporal violations, provide debugging aids with low overhead, and prevent vulnerabilities for buffer overflow attacks. So this has the same goals as Softbound, but this time with a temporal aspect. We'll first look at two temporal violations. The first is on the left, heap-based. You'll see that a pointer is first allocated, then a second pointer is put equal to the first pointer, and the first pointer is freed. But in the end of the program, you see that the second pointer is still used. However, the first one was freed. On the second, on the right, you'll see that main will call foo function. Pointer will be set to the to a local variable in the foo function. Once the foo function returns, the memory is freed. However, the pointer is still used in the main function itself, which causes another temporal violation. We'll fix this by making use of two concepts. The first one is identifier-based temporal checking. What you do is give a pointer a unique identifier, give a memory allocation a unique identifier. Pointers are associated with this unique identifier when they point to this memory location. So if a pointer tries to use a memory location that's already freed, it can be noticed with a unique identifier. The second concept is location-based temporal checking. You get again an extra field, an extra status field. So the memory location will get an extra status field. When a free is done on this memory location, you'll change the status field, and on a memory access, you'll check if the status, you'll check in status if the memory location was freed or not, and if it was, you abort. Now in CETS, this is done by temporal safety is done by combining these two concepts, and it's done as follows. You see again two extra fields. One is key and the other one is lock address. The basic concept is that pointers will get keys for a lock address, and you'll need a corresponding key to the lock address to access the memory. However, if the memory is freed, the lock address will change and pointers cannot access the memory anymore. You'll see two examples of checks to check if the pointers are indeed intact. The first one is checking for dangling pointers. So you'll see that the pointer key will be checked with the pointer lock address. If it's not the same, abort. Checking for double freeze is quite the same. You will check if the pointer is already freed or not, and if it is, abort. Finally, you'll see how these extra fields are saved. It's done with an extra table like Softbound, and this causes for an extreme condition for CTS, and it needs to have, and that is that it needs to have spatial safety. That is because the key and the lock address of a pointer need to remain intact and cannot be changed. Finally, there were some experiments done. Detection of temporal violations was 100% in a set of 30 programs, and it caused a minimal overhead of only around 84%. Finally, CTS was also tested in combination with Softbound. The result was that the pointer metadata had to extend to 4 words. The average runtime overhead was 116%, but there was detection of all spatial and temporal errors. This was our presentation about CETS and Softbound. I hope you learned a thing or two.